Good morning, everybody. It's a very great pleasure to be here in this wonderful architecture and this wonderful foundation, particularly because my field is astrophysics. And one of the many technological spin-outs from the sort of technology that is developed in programs that I've been managing over much of my life is now the basis for medical applications in vision and ophthalmics, which is a big local expertise. So the standard tools used in eye surgery are things that were developed by us to get clearer pictures of the universe. So it's an important point to remember in fundamental science is that all of the technology about which we've heard for the last day and a half, it was an accidental byproduct of what we were really trying to do, which is what I'm talking about today, which is the fundamental science. And in fact, we've heard a great deal in the yesterday and today about really complex things, people and their interactions and how much of a challenge that is. I have a much simpler task, which is simply to understand the entire universe. And it is simpler in a way, and it's also a subject in which we've been making spectacular progress. So the first question each of us has been asking is it meaningful to talk about a timescale of 100 years? And interestingly, it depends on, a true scientist's answer, it depends on when you ask the question. Turns out now is a very good time to be asking that question. In part because last Thursday was the 100th anniversary of the publication of Einstein's general relativity. In part because of the preceding 10 or 15 years led to the development of the whole of modern physics. So when famously in the year 1900, Lord Kelvin, the very great scientist, and gave an annual review of the state of science in 1900, he said, well, basically it's all done. There are a couple of things that we really need still to understand better, but basic science is done. Of course, so that wasn't a good time to be predicting the future. The reason for this is clear, and the reason why it's a good thing to do now, and that's from the triangle you can see up there, which is my cartoon summary of the invention of modern science, the age of the Enlightenment. So science, it was realized around the time of Copernicus and Galileo and Newton, requires moving around this entire loop. You start wherever you want in practice. If you don't start at the top left on observation, you end up becoming a philosopher and eventually decreeing that an old male is the center of the universe and must be obeyed, because that's essentially what every society did. But if you start up the top left with observation and say, what do I see, rather than what should I think, then you try to understand it, so you move over to explanation, and then you test your explanation by making a prediction, and then you observe. That is, in a trivial summary, the whole of the modern scientific method. And it works. We don't know why it works, but it works spectacularly well. And it's led us from feudal times through to the 50 quadzillion or whatever it is connected gadgets that we've heard about this morning. And the reason that we do this is summarized in the blue line there, is that the ideas then get their authority from whether or not they're effective at what they're attempting to do. Are they attempting to understand the universe or the nature of matter or how things really work, rather than because I was told. And there are two little summaries. One you got in more detail earlier of the methodology that we apply to do this, and that's mathematics. So as Galileo said, you saw the full quote later, the universe is written in the language of mathematics. Many, many people have made this statement since repeatedly. There's a particularly famous quote from Wigner, the unreasonable effectiveness of mathematics. And that title, The Unreasonable Effectiveness of Mathematics, has become something of a cliche, but it's true. Now, one of the things I'll come to at the end of my little presentation is that because we don't know why it's true, we can't predict its applicability in the future. And this is a really important potential limitation. And it might be that science, at least some parts of science, has started to address questions which actually cannot be answered by the scientific method. And that will be my last point. But to continue with the historical context and what science actually is, the really big advances in fundamental sciences have been when apparently different parts of nature have been realized to be actually different aspects of the same thing. And these are the really, really big advances that have created enormous new progress. Of those, the least technical, the one that most of you will know about, is Galileo and Newton unifying celestial and terrestrial physics. So gravity works in such a way that the moon is falling exactly as something on the Earth is falling, and it doesn't hit us because we've moved out of the way, and that's what we call an orbit, and that's all gravity is. It's as simple as that. Our next challenge, of course, you can see down the bottom there, is to unify quantum physics and gravity, because the other thing that happened just over a century ago was the development of quantum physics. And those two subjects then developed, quantum physics and gravity, developed in parallel and are still distinct subjects. But because they both describe the same basic properties of the universe at large, the expectation from starting purely from historical evidence, saying this is the way science works, is that there must be a single explanation, what my colleague Stephen Hawking calls the grand unified theory, which in some way will connect quantum physics and gravity, and I'll show you a little more about that in a minute. But one of the things that has come out of modern science in particular, that people find it very difficult to come to terms with the sort of fundamental concepts of what nature is really like. This is part of what we call the Copernican principle, and that we grow up, common sense applies, we learn how to interact with the world around us, we learn what makes sense. So we then develop from that a series of expectations. So if you look at that sculpture there by Jean Dante, everybody here would say, okay, I know what that is. Time has passed. There is an old person and a young person. So this is a microcosm of the way time behaves. And we expect, for just as one simple example of the complexity of modern science, that is the way it always is. Time goes in one direction. Well, it doesn't, nor does it all go at the same speed. So in fact, the bottom picture there is the heart of the Large Hadron Collider at CERN. There's a person there for scale, if you can see him. So that is the equivalent of the monastery over the road. This is our great modern cathedral, designed to probe our knowledge and belief of how the universe is structured. And as you can see, I've written there, particles in the Large Hadron Collider move so fast that relativistic effects become very important. So in fact, those particles, when we watch them, seem to us to be living 7,000 times longer than they seem to live as far as they're concerned. So these particles that are created in the Large Hadron Collider are very, very radioactive, to slightly misuse the term. They're very unstable. They live for very, very short times, tiny fractions of a second. But they're moving so fast that time for them seems to slow down, and so they're able to travel very much further than they should be able to travel before they decay. In fact, they can travel far enough that they get out into the detectors and we can see them. But this room, for example, is full of cosmic ray muons being created when high-energy atoms hit the top of our atmosphere and they come down to the Earth. And those things live in there, as far as they're concerned, they live for about 1/10 of a second. And in 1/10 of a second, they should be able to travel a kilometre or so. In fact, they've travelled 20 kilometres, and so are right now literally in this room. The flashes people see in their eyes sometimes are caused by these things. They're particles from outer space decaying in your eye. And the reason they get down to us is because they're travelling so fast that, as far as we're concerned, they live longer than they should, and they live long enough so they get here. So it's not an illusion. It's not that the clocks are wrong. You really do see those flashes in your eye, and that's the way nature works. And it's an example of how counterintuitive is our deep understanding of nature and physics. Now, let's look briefly at where that came from and why one is today confident that one can talk about the future. I've listed there the 5 big advances in what we now call elementary particle physics, associated with the names of the people underneath them. The two things to notice on this slide. The first is that each of those big questions, like what connects electricity and magnetism, now this is something that was just observed experimentally. We create electricity by moving magnets. That's how all the electricity that runs our gadgets comes from. It was observed this was true. The explanation of why it works is a set of equations which predicted an elementary particle, in fact the particle of light, because light is part of electricity and magnetism. Similarly, I'll read just one more. How do I combine special relativity and electromagnetism? Well, that's what's called quantum electrodynamics. It was done by Dirac and led to a prediction of not just one particle, but a whole families of particles called antimatter. And each of those other questions there have similarly some very sophisticated mathematics and a very simple prediction of a new particle. The most popularly known one is perhaps the most recent, the origin of mass. Why are you heavy? Now, again, common sense doesn't tell people to ask that question. Why are you heavy? Well, of course I'm heavy. Everything's heavy, right? It's just what nature is. But no, it's not. A lot of things are not heavy at all. And the answer to that is what we now call the Higgs field. Got a slightly different technical name in the trade, but it doesn't matter. And just a couple of years ago, the predicted particle was seen, the Higgs boson. And in those pictures along the bottom there, you see why it was that by the time of the century ago, when Einstein's general relativity came out, quantum mechanics and electromagnetism had developed sufficiently that people knew there were atoms, these atoms had structures inside them, and that in some way the different forces of nature could be reconciled to produce a deeper understanding. And so by 100 years ago, that was clear what the future of what the 20th century of physics was going to be. It would be going to answer those questions. In fact, it took only 50 years. And although we think of the Higgs boson as a big, recent discovery, it was actually predicted more than 50 years ago, in the early 1960s. And we've made no progress at all, theoretically, in the last century. Lots of technical stuff's been done, but nothing fundamental. The other important thing about that picture is, although the Planck looks fairly old there, because people did in those days for some reason. And Maxwell looks old because he's got a beard, but he wasn't. Those great advances were all made by people in their 20s. And this is the other important lesson. It's all very well for us old guys, grey hair, sitting at the front here giving these talks. It is people in their early 20s who make the really great advances in sciences. And so that is the fundamental lesson, which I'm sure is not going to be different 100 years from now. The future, in a very non-trivial sense, lies with the young. But there's also a clue at the top there that we have this fantastic model, but it only works well for a small subset of reality. And so in the last 50 years, although we haven't been advancing particularly in fundamental understanding, we've made spectacular progress in the observation part of the triangle, the balloon triangle. And in particular, we now know that the universe is not made of what it seems to be made of. So that pie chart there shows you the content, the energy content of the universe. And in yellow is all the ordinary matter, the stuff of which we are made. As you know, we are stardust. We're made essentially of water. The hydrogen in that water was created in the Big Bang 13.7 billion years ago. The oxygen in that water was created when a star roughly initially 10 times the weight of our sun exploded at the end of its life and dispersed this oxygen into the interstellar medium, along with the carbon and the nitrogen and everything else that came with it. And so the stuff of which we are made was once inside a star or was once inside the Big Bang. So we know we're intimately connected. We've worked all that out over the last half century, but we've also realized that actually that's impressive. It's nice to know who your ancient ancestor was. It was a star. But it's also amazing because that turns out to be almost insignificant compared to what's out there. So if I weigh the galaxy, which I did once, I realized that actually there's about 5 times more matter of a different sort in the galaxy, in our Milky Way, than there is of the stuff of which we are made, or which stars are made, or which planets are made. There's some completely different form of matter. And it shares no relationship with everything that we know and understand, except one, that it knows about gravity, which is why we call it matter. Matter is something that generates and responds to gravity. That's our definition of it. But there's 5 times more of this stuff out there than what we're made of. And so, in a very real sense, we are insignificant and irrelevant compared to the universe. It's a natural extension of the Copernican principle. We're not really at the center of anything. In fact, we're not even made of anything particularly interesting. But we don't know what that dark matter is. So that's a great challenge for the next century. The other great discovery from just over a decade ago was that the universe is accelerating. So there's something out there that's pushing against gravity, some natural force which it seems is just an inherent property of space-time itself, that space-time pushes itself apart. We have absolutely no idea what this is. It's called dark energy, but that's just a label. Actually, it's a rather clever label because it was designed to make cosmology funding eligible for funding through the energy program in the US, and that's why it's called that. It's got no other reason at all. We don't know what this stuff is. So we know what science is going to be doing for the next century. It's been explaining dark matter and trying to understand dark energy. And we've even got a fair idea of how it's going to go about, how it's going to be put together. So what I've shown there is a little summary of the entire history of the universe up till now. And you can see in the middle cartoon that after some beginning, some event, which literally was a beginning. Before that, there was no space-time, there was no space, there was no time. There was some sort of quantum foamy structure that we have yet to understand. Then a large amount of energy, perhaps just by chance, appeared in some place and was too much energy to just annihilate itself again, and so popped into existence, and that's us, that's our universe. Then this universe started expanding at hundreds of thousands of times the speed of light. It is possible for a universe to do that. It's not possible for us to move that fast, but universes have different rules. And it carried on doing this for what by its standards was a long time, many, many lifetimes. But by our standards was about a quadrillionth of a second, but that was enough. And so the universe then stopped doing that. Why, we don't know. And then it just carried on its expansion. But because the universe had some matter left in it, stuff of which we are made, that matter has gravity and it slowed down the universe. And so this slowing down, the universe slowed down gently until about 5 billion years ago, which coincidentally, probably, is around the time our sun and our Earth was formed. And around the time that our sun and Earth formed, this new force, which we call dark energy, took over and started speeding up the expansion of the universe again. So instead of it slowing down, and the big question of most of my working life was, will the expansion of the universe stop and fall back into a big black hole again, or will it just carry on forever? Well, now we know it's actually speeding up. It's going the other way. And it's getting faster and faster. And so if nothing much else happens, then, and if that is that force, whatever it is, doesn't know about time, then this will carry on forever, and the universe will get spread out and spread out and spread out, so much so that most of the things in the universe will be so far away from us that their light cannot travel back to us in the age of the universe. So stuff will fall off the horizon of the universe. Still there, we just won't see it. So our universe is getting more and more empty. And eventually, if this goes on long enough, our universe will become completely empty, and the entire universe will contain one elementary particle. And every other elementary particle will be in a universe of its own. And in the long term, the long-term fate of the universe is what's called a heat death. So it's another way of phrasing it would be a loneliness death. There'll be nothing out there at all, or we will have no knowledge or consciousness possible in such a universe. But maybe that's not what's going to happen. We don't know. Maybe that, like the first time this happened in the universe, maybe that acceleration will stop eventually. And gravity will take over again. We have no idea. And on the left there, you can see drawn as a pyramid, the contents of the universe, with the stuff which we understand being that tiny little green thing up the top, and all the rest of it being the challenge for the next century. And it's particularly challenging to know what to do. How do we make progress in this case? Well, we have absolutely no understanding of why the universe is like this. All of our theories are dynamical, all of general relativity, all of quantum mechanics. They can tell you that if I start from here, what will happen in the future, and you can extrapolate back a bit and say what was there before, and so one can do that. But there's no explanation, there's no why, there's not even a how, it's just a what. And so because of that, we can't predict what's going to go on. And this leads us to this rather intriguing situation, where in the bottom two pictures, rather pretty ones, you can summarize what we've learned in the last century, which is a spectacular amount. So we understand the structure of the very small in exquisite detail. It's possible to calculate what is happening inside the Large Hadron Collider to a completely ridiculous number of significant digits. And in the left-hand side, we know surprisingly accurately, impressively accurately, what happened in the very early universe from times when it was about maybe 100 billionth of a second old. That first tiny bit we haven't got right yet, but all the rest of it, we know exactly how all the particles came into existence and how they got to be in us, because that's the sort of physics we can do in our lab. But the big unknown there, of course, is, well, what about all the stuff that this doesn't describe at all, which is most of it? And for here, perhaps we get a clue from the fact that dark matter exists. We know it's there, we measure it, and probably it's made of some sort of elementary particles, some mix of them, the same as ordinary matter is made of them. And if you go right back to the slide I summarized the history of the development of big ideas in physics, every time we had a big question, like what is matter? How do I combine relativity and magnetism? The answer was some complicated mathematics and a new particle. So it's an interesting historical extrapolation that all these dark matter particles are actually the answer to some really interesting questions that we haven't asked yet. And there are lots of questions we can know, like why does time go in one direction? It doesn't at the microscopic level. Particles go backwards and forwards in time all routinely, that's what they do. But big things don't. There's questions we believe we've answered, like why are you heavy? But there are other things about what was there before the beginning. What happens when I combine gravity with quantum mechanics? Presumably, each of these things is a theory that will lead to some complicated mathematics and predict new particles, which actually we've already seen. So in a very real sense, the fact that we have discovered dark matter is evidence that the historical development of the fundamental sciences will continue, though we have yet no real clue as to what the answer is. And in fact, I suspect that the answer to the cold dark matter problem will be known well in under 100 years, probably nearer 10 or 20 years. People will actually start finding the particles. And on the same timescale, and I haven't bothered to put it on the slide, because our entire lecture theatre here is surrounded with alien worlds. Alien worlds are being discovered at an industrial rate in astronomy these days. And so certainly within 2 or 3 decades from now, we will know if life is ubiquitous in the universe. Planets like Earth, with water on them, so we've already seen the water, are being discovered at a great rate. And one of these days we'll see one of them go green in summer and white in winter or something like that, and we will know that in a very real sense we're not alone. The consequences of that for philosophy and psychology remain to be worked out, but exobiology will become a real subject, perhaps studied in places like this. But for my last slide, the more fundamental stuff, what about the structure of space-time? What's really going on? Well, what we anticipate, this grand unified theory I mentioned, there's a cartoon concept of it there, is that, again, extrapolating from history, as one looks more closely at different forces, for example, electricity and magnetism, you see, oh, they're really just different aspects of the same thing. They seem to us different because there's not much energy and we're not looking on the right scales. If I look more fundamentally, I can see it. Similarly, several of the other forces have been realized to be just different aspects of the same more fundamental force when we look closely enough inside elementary particles. And the expectation is if we can just go down about 1 trillion times smaller than an elementary particle, all these forces will come together. But at that stage, we're well deep inside the world where quantum effects are dominant, and so our current theories don't allow us to calculate inside there. And possibly even, and this is why unification is called grand unification, that gravity will even appear. So when one is on a very, very small scale, gravity, the special thing about gravity is so weak, it's pathetically weak. You know, the chemical forces in your body hold your body together, but all gravity can do is keep you comfortable in a chair and you can stand up and walk around. So gravity is ridiculously weak. That's one of the answers. It's one of the questions whose answer is probably a particle. But on the very, very, very small scales, it's called a Planck scale, probably even gravity will come together. And there is one class of theory which is being developed called string theory, which is starting to make progress towards this. But it makes a very strange discovery, which goes back to my beginning point, is that possibly it's not even a science. This same unification not quite predicts, but is consistent with some of the predictions, that there are actually many universes. So it's a phrase used as multiverse, and so there's a cartoon view there of our little universe being a tiny speck on just one universe, which is just one among an infinite number of universes. And as I mentioned earlier, if inflation carries on, our universe is going, we know that there'll be other universes because all the stuff we can see today will be out in its own universe. Now that then raises a very philosophical point. If our fundamental theory that predicts the way that nature and space-time work predicts things that are in principle unobservable, it predicts that most things, essentially an infinite number of things, are beyond our ability to ever study or detect them, then we've broken the triangle. We no longer have a verifiable prediction. And so it is quite possible that 100 years from now we will have realized that we have a tentative answer to what is the universe and why is it, but we will have no way of ever knowing if it's a unique answer. So it might well be that that one question falls out of science. Thank you.